In this video, we'll be looking at a logic circuit and generating the truth table for that logic circuit. The first thing we want to do is build the foundations of our truth table. So first of all, we're going to take our three inputs, A, B, and C, and we're going to have our output, Z. Between our inputs and our output, we have these 5 gates. These 5 gates will all be given their own letter, D, E, F, G, and H. Now let's start adding this into our truth table. We're going to start by having our 3 inputs, our 5 gates, and our output. Now we're going to first of all add in all of the possible input combinations to our circuit. The amount of possible input combinations to a circuit will be the same as 2 to the power of the amount of inputs. Since we have 3 inputs, that means our amount of possible combinations are 2 to the power of 3, and as we all know, 2 to the power of 3 is 8. So let's add our 8 possible combinations. What I'm building here will be very familiar to you, because I'm simply building a binary table. I suggest looking at what a binary table is before moving on with this exercise if you don't understand what a binary table is. Next we're going to be looking at gate D. Gate D is an AND gate. This means all 3 of its inputs need to be turned on for it to output. D is connected up to A, to B, and to C. So when all 3 of A, B, and C are turned on, D will also be turned on. From our truth table, we know there is only one possible situation where A, B, and C are turned on, which is our bottom row here. So we know our bottom row, D will be turned on, and for the other 7 rows, D will be turned off. Next we have 2 NOT gates, E and F. A NOT gate will invert the current coming into it. So if a negative current is coming in, it will become positive and vice versa. E is connected up to B, which means anywhere on our truth table that B is possible, B is positive, E will be negative, and vice versa. So let's add that to our truth table. Where B is 0, E is 1. And where B is 1, E is 0. We can now do the same for F and C. Wherever C is positive, F will be negative, and vice versa. So let's add that to the truth table. Where C is 0, F will be 1, and where C is 1, F will be 0. Next we're going to be looking at G, our OR gate. An OR gate will output as long as it has at least one positive input coming in. So as long as either E or F are positive, G will also be positive. So let's take a look at our truth table and write that in. In our top row here, both E and F are positive, so G will be. In our second row, E is positive, so G will be. In our third row, F is positive, so G will be. In our fourth row, both E and F are negative, so G also will be. And it is the same for the next 4 rows. Now we're going to be looking at H, another AND gate. As previously discussed, this gate will output positive as long as all of its inputs are positive. H is connected up to A and also up to G. So where both A and G are positive, H will also be positive. So in our top row, in our top 4 rows, A is never positive. So H will also never be positive in these top 4 rows. In our bottom 4 rows, A is always positive. So let's look at G in these next 4 rows. G is positive for the top 3 rows here, so that means H also can be, because in these 3 rows, G and A are positive. G is negative on the last row, which means H will also be negative. Lastly, we have Z, our output, which is an OR gate. Of course, an OR gate will always output positive as long as it has at least one input that is positive. It is connected up to D, and it is connected up to H. So as long as either D or H are positive, then Z will be positive. So let's take a look at our truth table and add that in. In our top row, neither D or H are positive, so Z will be negative. In our second row, the same, neither D or H are positive. And for the next two rows, this is also the case. D and H are both negative for these two. On our next three rows, H is positive here, H is positive here, and H is positive here. So Z will be positive for these three rows. On our last row, D is positive, so Z will also be positive. Now that we've completed our truth table, we can remove all of the gates from the table. They are no longer needed. This leaves us with our final truth table. A, B, C, and Z are now all completed on our truth table. We can see that when A, B, and C are all negative, Z will be negative. When only B is positive, Z will also be negative. And for all of our instances where A is positive, Z will be positive. Let's create this in logically and see if our truth table matches up. Here is the same circuit created in logically. If we take a look at the truth table for this, we will see false, 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 true, 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 which matches our 0, 0, 0, 0, 1, 1, 1, 1 that we expected. This means the truth table we have created for this circuit is an accurate reflection. I hope this helps, and of course if there is anything else I can do to help, please let me know. Thank you.